All right. Good morning, everyone, and welcome after a nice weekend. I did upload the solution to exam one as I promised. Okay. Today we're going to start a new chapter called Chapter 5, Stability. Stability is an important part of any time varying system. So we're gonna, in general, let's take a look at xn plus 1 equal 1/2 xn with xn naught equal x naught. Then the solution is xn equal to x naught times 1/2 to power n minus n naught. Remember, n naught is fixed. And as n goes to infinity, the lim as n goes to infinity of xn equal the lim as n goes to infinity x naught 1/2 to power n minus n naught, and that is x naught times 1/2 to power infinity, and that is 0. So the solution goes to 0. All right. Well, what happens if the system is nonlinear that you cannot solve? Notice that x of n equals 0 is a solution, provided that x naught equals 0. For example, if you put, because you get 0 equal 1/2 times 0, which means 0 equals 0. So xn equals 0. And notice here, as n goes to infinity, where does this go to? 0, which is this one here. Okay? So this xn equals 0 is called equilibrium solution, or constant solution, or a fixed point. So we're gonna consider the system xn plus 1 equal to fxn. So this is a function of x. And this is 5.1.1. And f is from R into R, that is continuous. Continuous in x. Okay? For example, in xn plus 1 equal 1/2 xn, here, f of xn is 1/2 xn. You see that? Okay. Now, definition, we say x star is a fixed point or equilibrium point or a constant solution of 5.1.1 if f of x star equal x star. Okay. Hence, to find x star, just set x equal f of x and solve for x. Now, where did this constant solution mean? Let's take a look at this. This can be written as del xn equal xn plus f of xn. So constant solution means no variation in the solution. Or del xn equals 0, which implies xn plus f of xn. Oh, this is minus, sorry. Minus. Equals 0, which means xn equal to f of xn, or short, x equal to f of x. So you see where this came from? Constant solution. Okay? All right. So a little bit ago, we had xn plus 1 equal 1/2 xn. So x equal 1/2 x means 2x equal x, or x2, sorry, or x equals 0. So x star is 0. And we already know that, okay? All right. What about if xn plus 1 equal 2 plus 1/2 xn? So let's say we want to find the solution. We want to find the constant solution, equilibrium solution, or fixed point. So we have x equal f of x implies x equal 2 plus 1/2 x, correct? So that means 1/2 x equal to 2, or x equal 4. So x star is 4. So this has a fixed point, or a constant solution, equal to 4. All right. Now, reason for it called fixed point. Suppose we let x of 0 at 0 equal 4. Then what is from here? x1 equal 2 plus 1/2 times 4, and that is 4. What about x2? That is 2 plus 1/2 x1. That is 2 plus 1/2 times 4, and that is 4. What is x3? Is 2 plus 1/2 x2. That is 4. and then you will get xk equal 4. So if you choose your initial point to be the equilibrium solution, you will never leave. You will always be at the fixed point. So if we choose x naught equal 4, which is x star, then we never leave x star equal to 4. Okay? You will stay on it for all n. That is the solution. All right. Any questions? Now, if the fixed point x star is different from 0, then the translation x star of n equal xn minus x star, okay, will translate x star to the origin. Okay, we'll bring it to the origin. Why? Because for x star, for x equal x star, this is 0. So let's take a look here. So we're gonna have x star of n plus 1, okay, plus x star equal to plus 1/2 xn plus x star. Okay? And so equal to 2 minus 1/2 x star plus 1/2 x star of n. Okay? And then this will bring us down to the solution being 0. And let's see, 1/2 xn plus x star. And that will bring the solution down to 0. Yeah. Okay. All right. So, for example, here, in this one, x star is 4, correct? Do you remember that? Because what did we do? We said x equal 2 plus 1/2 x. So we got 1/2 x equal 2, x equal 4. So x star is 4. So put it in. Equal 2 minus 1/2 times 4 plus 1/2 x star of n. And that is 1/2 x tilde of n. So if you put x tilde equal f of x tilde, you will get x tilde equal 1/2 x tilde, which implies x tilde star is 0. So we brought it to the origin. You see how we did? So any critical point that is not at the origin, you can always do a translation, a new variation, this one, that will bring it to 0. In this case, so when x star equals 0, we say the 0 solution. So in other words, if I have xn plus 1 equal f of xn, so means, so to talk about the 0 solution, we must have f of 0 equals 0. Why? Because 0 equal to f of 0. So these two are not equal unless f of 0 is 0. Okay? Then in this instance, we say 0 is the solution. So, because it will be easier to talk about the 0 solution than the other solution. Okay? All right. Now we want to study the stability. We want to study the stability of 5.51 at x star. We will define this later. Okay? All right. Any questions? So we're gonna perturb x star by an amount eta function. So that this is perturbation term. So in other words, I'm gonna have xn equal to x star plus eta of n. Remember 5.1 xn plus 1 equal f of xn. Okay? So we are going to do a Taylor series around x star. Okay? All right. So xn plus 1 equal x star plus eta of n plus 1. And that is f of x. That will be x star plus eta of n. And we're going to do the Taylor series about x equal x star. So that is going to be f of x star plus f prime, okay, of x star over 1 factorial times, what do you think it is times? X plus eta minus x star. Okay? But I am doing it at x star. So I'm going to replace this one by that. A plus f second of x star over 2 factorial times x star plus eta minus x star squared plus plus plus. Okay? So that is f of x star plus f prime of x star times eta. Okay? Plus f second of x star over 2 factorial times eta squared. Okay? So we are here. This one is equal to that one. Do you see that? Okay. So we have x star plus eta, eta plus 1 equal to f of x star plus f prime of x star times eta of n plus f second of x star over 2 factorial eta squared of n. But this one is x star. So we have eta of n plus 1 equal f prime of x star plus times eta of n. Okay? So now we're gonna assume that, okay, so we're gonna assume that f prime of x star times eta is way bigger than f second of x star eta squared. And so this is plus O of eta squared. So we're gonna solve this system here. So we have eta of n plus 1 equal f prime of x star eta of n. All right. So which has the solution eta of n equal to some constant f prime of x star to power n. Okay? So if we let s equal f prime of x star, then eta of n is c times s to power n. And we will see, c is some constant. We will see that eta of n goes to 0 if s is less than 1, and eta of n goes to infinity if s bigger than 1, and no information if s equal 1. So in this here, so here we say x star is asymptotically stable. And we will talk about it in a second. Is asymptotically stable because it goes to 0. Here it is unstable. That means solution go away from x star. Okay. Any questions? So let's take a look at a couple examples. So you see, before we saw xn plus 1 equal to 1/2 xn, and we will see here f of x is 1/2 x, and s is f prime of x. That is 1/2. And here we know that x star equals 0. And so s is 1/2 less than 1, then x star equals 0 is asymptotically stable. Okay? And we already know that if the solution goes to 0. All right? Let's take a look at xn equal to x squared of n, xn plus xn plus 1 equal to x squared of n. All right, and we see here x equal to x squared means what? Mean x minus 1 minus 2x equals 0, x equals 0, and x equal 1/2. Correct? So we have two, we have x star equals 0, and we have x star is 1/2. So in our case, f of x is 2x squared. All right, so f prime of x is 4x. So at x star equals 0, s is f prime of 0. And what is that? That is 0 less than 1. So x star equals 0 is asymptotically stable. Okay? And at x star equal 1/2, s is f prime of 1/2, and that is 4 times 1/2, that is 2 bigger than 1. So x star equal to 1/2 is unstable. Okay? All right. Any questions? Okay. So let us, before we state a couple definition, all right. So let's take a look at xn plus 1 equal f of xn. Okay. And with x0 equal x0. So let's 5.11. So what is x1? x1 is f of x0. What is x2? Is f of x1. That is f of x0. That is f squared of x0. And if I keep going, okay, so if I keep going, then I will have x0, f of x0, f squared of x0, and so forth. And if we set f0 of x0 equal to x0, then we have the set x0 where n belong to n of n0 is called an orbit. Is called an orbit of x0. Okay. So this yield, xn plus 1 equal to fn plus 1 of x0. Okay. And that is f of fn of x0, and that is f of xn. Okay. Okay. So basically, you're iterating around the the initial condition. Okay, so we have the following definition. So definition, if x of 0 equal x0, then x star is a stable if for each epsilon positive, there is a delta equal delta of epsilon positive such that x0 minus delta less than epsilon implies, okay, implies fn of x0 minus x star is for less than, oh, this is, sorry. This is x0 minus x star less than delta and imply this less than epsilon. There is a delta that depend on epsilon, okay? All right. So B unstable if it's not stable. Okay. And asymptotically stable if x star is stable and the limit as n goes to infinity of xn goes to x star. Okay? All right? So, based on this definition, we have the following theorem. All right? Let x star be a fixed point of 5.1.1, then A x star is asymptotically stable if f prime of x star is less than 1. B, x star is unstable if f prime of x star is bigger than 1. Okay? There is no info about x star if f prime of x star equal 1. Okay? Any questions? Any questions? All right. Let me take an example. This is example 5.3, population growth. So we're gonna assume the population is given by big N equal R to N of N times 1 minus N of N over K. And K is positive. Okay? So here, R positive is the growth rate, and K is the environment capacity. Okay? Now we want N of N plus 1 to be positive for all N, Otherwise, the system doesn't make sense. So that means that implies 1 minus N over K is positive. That means N is bigger than K. Okay? No, less than K. Less than K. All right? n of n is less than k. So in order for this to be feasible feasible system or feasible model, well, we want the population to be almost positive. All right. And so so this is nonlinear. And impossible to solve. Okay. So let's look for the critical point. So let's look for fixed point. Remember, I'm using the word fixed point. In the book, I may use equilibrium solution or constant solutions. They are the same. I emphasizing all three because it depends on what you are reading. It depends on the source. So to be safe, I try to cover all of them. All right. So we have here f of n is r n times 1 minus n over k. So n equal f of n implies n is r of n 1 minus k over n. All right. If I multiply by n, I get n squared. How do I want to do that? Let me factor n out. That will be 1 minus r times 1 minus n over k equals 0. Okay? So that is n equals 0 means 1 n star is 0 and 1 minus r1 minus n over k equals 0. All right. And so if I take how I want to do it, if I take 1 minus r minus rn over k equals 0, multiply by k minus kr minus rn equals 0. All right. So that means k1 minus r equal rn. That means n is r1 minus r over r. Okay. Sorry, what happened to my k? Okay. Okay. And you see, we want n to be positive, so we must require the growth rate to be between 0 and 1. So we have n star equal to k1 minus r over r for 0 less than r less than 1. Okay. Did I make a sign mistake somewhere? Okay, let's see. F of n equal r n capacity n between less than k or n 1 minus n over k. Okay, let's see. So we have Fn equal Rn 1 minus n over k. So n equal Rn 1 minus k over n. So I'm gonna have n minus, oh, okay, see, we made a mistake here. This is a plus. So this is minus. So over minus. So this is R minus 1 times K over R. Okay? We found the mistake. When I multiplied by minus through, I did not change this. So now it's K minus KR plus Rn equals 0. Factor K here, take minus Rn over there. Then N is K1 minus R over minus R, that is R minus 1 over R times K. So now we want this to be positive, so this is a positive only for R bigger than 1. Okay? All right. Well, it makes sense. This is the growth rate. So if it's less than 1, then the population will die. That's why I got suspicious. Okay, so we have n star equal to 0, and we have n star is R minus 1 over R times K. And we needed R bigger than 1. Okay? Okay, now this is Fn. So what is the derivative of that? So we need to look at f prime of n to apply our theorem. All right? So this is f. So this is Rn minus, okay, Rn minus Rn squared over k. So f prime of n is R minus 2R over k times n. Okay? So that is f prime. So now for n star equals 0, f prime of n star equal f prime of 0, and that is R. Okay? All right? So, well, that is really good. And so that is bigger than 1. So n star equals 0 is unstable. Can you tell me if for a biologist, would he like this or not? Would he like that n star equals 0 be unstable or stable? What do you think? Now I really need your input. What do you think? What does n star represent? N star represent a population, correct? So does the biologist want, after a long time, all the solution, which means the population, go down to 0? Does he like that or not? Well, of course, the answer is no. Because if n star equals 0 is stable, that means the whatever solution the biologist is studying will go into extinction. Do you understand the meaning here? The population will go into extinction. So the biologists pray hard that n star equals 0 is unstable. Okay? Any question? Did you see the meaning here? All right. So, and notice this is R 1 minus 2 n over k. Now we're gonna do the other n. For n star equal R minus 1 RK, we have f prime of n star equal to R times 1 minus 2 over k times n times R minus 1 over R times k. Okay? And that is 1 minus 2 times R minus 1. Okay? Okay, so this is 1 minus 2R plus 2. Okay?
Professor,
Yeah.
that R is being multiplied to 1 minus and then that mess. What happened to that R times the first one there?
Oh, thank you. Thank you. That is all. Okay? Is that what you meant?
Yes.
Yeah. Thank you. So what do I have? I have minus R plus 2, correct? Okay? All right. So let us study it carefully. So we need f prime of n star in absolute value. That is let me put it here, that is 2 minus R. It is 2 minus R. Now remember, R is between what and what? R is bigger than 1, correct? So that is less than 1 for 0 less than for R bigger than 1. Okay? Well, how big? How big is this? Well, I mean, if I take R equal to 3, that will be 1. So basically, 1 less than R less than 3. Okay? So in this case, and the star, which is what? R minus 1 over R times K is asymptotically stable. Okay? Do you see what happened? Because if I let R go all the way, if I take R equal 4, that will be 2 minus 4 in absolute value. That will be 2 bigger than 1. That will be unstable. And then it's unstable if R bigger than 3. All right. Now, in the book, I take a look at so in figure 2.4, let's see. Okay. So you can see on page 172. On 172, I take K to be 1. That's okay, because I wanted to simplify my system. And then with different values of R, it's still the same R. If I take it to be 3.2, in A, we have R is 3.2 and so forth. And you will see different values from R equals 0. You see, I'm looking at these graphs here, and I want to explain what this graph means in a sense. So let's take 5 minutes break and come back, because I'm going to move on to different things. All right, I'm back. Um,
Hey,
let-
Professor,
yes.
I do have a question. I just know in like a lot of differential equations classes, like if you have a bound for something to be stable, wouldn't that be just conditionally stable, or is it always just asymptotically stable?
No, it's not asymptotically stable. For example, um, let's take xn plus 1 equal xn with x of 0 equal 1. You see what I mean?
Yeah.
So what is the solution to that? The solution is xn equal to 1. Correct?
Yeah.
To 1 to I mean time. Okay, let's say x0 equal x naught. So xn is x naught times 1 to power n, and that is x naught, correct? So this is a stable. So x naught is stable. That is x star equal to this solution xn. So what is, so x star, may I say, so this is x, or xn equal x0 is the stable. Okay? However, the limit as n goes to infinity of xn equal to x naught. So if x naught is not 0, this is different than 0, this is not asymptotically stable. You see what I mean? Does that clarify things?
Yeah, a little bit. I just like like if you vary R in the example we just did,
Right.
there's bounds on what makes the solution stable. So I just was curious if that I just was curious why we weren't calling it conditionally stable. But I see what you
No,
mean.
no, we don't. We don't have that's definition. I mean, we have to accept the definition.
Yeah, I get. Okay, that makes sense.
Yeah. So, I mean, you want to call it conditionally stable. Well, I mean, or I mean, you know the growth rate. So basically, you give the biologist more information, right? You say, hey, if R is bigger than 1, then you have a feasible solution. You have a feasible system. First of all, you want your system to be well posed. Remember, this is represent population, so the solution could never be negative. And it turned out it's never negative as long as R is bigger than 1. Okay? And so now, what about the stability with respect to R? It turned out that if R between 1 and 3, it's asymptotically stable. If R is bigger than 3, it's unstable. Okay? Which is good enough. All right. Now we're gonna look at some phenomenon called the staircase method. Staircase method. Let us take a look at xn plus 1 equal 1/2 xn. We know that x star equals 0 is a stable. Okay? So what we're gonna do is, this is 1/2 xn. Okay? This is 1/2, and this is xn. Okay? So if you start here, this is x star equals 0. If you start at anywhere here, you move up to the curve. So here, f of x is 1/2 x. So this is f of x, and this is y equal to x. So you go to this, you go from here to the solution, and then from here you go vertically toward this line. Then you move down, you go this way, you move down, you go this way, you're gonna end up at x star equals 0 is a solution. So you see what happened? And you may say, I want to start, even if you start here, you go this way, come back here, go down, come back, and then you're going to end up there. So this is called the staircase. So at your first point, you go vertically to the solution. So you go vertically to f, then horizontally to y equal x, and repeat this process. Okay? You will repeat it. So let us talk about something different. Let's talk about xn plus 1 equal rxn times 1 minus xn. Okay? So we know for k equal 1 here, so we know x star equals 0 and x star equal to r minus 1 over r. Okay? And you want r to be bigger than 1 in order for this to be feasible. So here, f of x is rx 1 minus x. Let us study this one here. Okay? Now, this is a parabola that goes like this. That is f of x. And so this is f of x. Okay? To be able to do better job, so now r. So let r equal to 2. So let's see what happened. So you have f of x equal 2x 1 minus x. And then an x star is 2 minus 1 over 2, that is 1/2. And now let's take y equal to x. So they're gonna intersect. Actually, they're gonna intersect, sorry. They're gonna intersect here at 1/2. Okay? So what do we know? We know this and we know this. These are two equilibrium solution. All right. Now, let us start to the left of 1/2. Okay? All right. So where am I gonna go? Let's start at anywhere here. I said we go straight to F. Do you remember? We go straight to F. Then what do? We go horizontally to this. Then we go up to here. We go like this. We go up like this, and then this is stable. So X star equal 1/2 is asymptotically stable. But everything is running away from 0. And this one is X star equal 0 is unstable. Okay? And this is very well done in the book. You can look at it and try to get some information out of it. All right? Any questions? And then in the book, I do. So this is called the staircase method, is well explained in the book. I need you to look at it. And there is a place in the book where I do this one for different value of R. This one here, again, is very, very interesting to see it. And I seem like I want to find it, and I can't now. Oh, there. Okay. Any questions? All right. So this is that. This is the theorem. And okay. All right. So let me get more of my notes. Okay, so I want to do a more definition, but I need a concept called a norm. So I'm gonna go on to 5.2 system stability. So we're looking again at xn plus 1 equal to f of n xn, xn naught equal x naught, and this is 5.2.1, and f from 0 infinity cross d into Rn, and d is a subset of Rn, and it's continuous. So a vector x star belong to Rn is an equilibrium point, equilibrium solution constant solution or a fixed point of 5.2.1 if f of n x star equal to x star. So the same definition as before. So now we have a norm here. So we're going to talk about the solution. Okay. And then if X star is different from 0, 0 all the way to 0, it's not the zero solution, then the transformation will be Xn minus X star, okay? And will give Xn plus 1 equal to Xn plus 1 plus X star, which is equal to F of n plus X star. And so equal to minus X star plus F of n and this will be G of n X of n, okay? And in this case, X star of n equals 0 is an equilibrium solution of 5.2.1. So like what we did for the scalar case. Okay? So now we're going to talk about the zero solution. So now we say X of n equals 0 is a zero solution of 5.2.1 if F of n 0 equals 0. So for example, if I have Xn plus 1 equal n times X squared of n. Okay? And F of n Xn here is n X squared of n, and F of n 0 equal n times 0 squared, that is 0. So Xn equals 0 is a zero solution. If not, translate it. Okay? If not, translate the solution by using the translation. All right. So oops. Bear with me a second.
Well done.
No. Are you leaving?
Yeah, I'll be back.
Oh, I thought you're going to Tennessee.
No.
All right, good. All right. So what did we do today? So today we talked about the same concept, but we talked about it for a scalar function, scalar function. Now we're gonna talk if we have systems. Okay, definition. This is a norm. A real valued function on a vector space V is called a norm. And denoted by whatever goes in denoted by X, sorry, if it has the following property. Okay, one, X is bigger than 0 for all X not 0 in V. 2, X equals 0 if X equals 0. 3, alpha X equal alpha X for all alpha in R, and X plus Y less or equal to X plus Y, and X, Y belong to the vector space V. So this is the definition of a norm. And here are example of norms. Let's say X is X1 to Xn. This belongs to Rn. Okay? Then A is a norm if I go with X to be the max 1 that's equal to I that's equal to n of xi. So I look at all these numbers and I take the absolute value of them, and then the maximum is the norm. Another norm, B is, okay, so this pen go away. Let me get another pen. Wait a minute. And this one is I equal 1 to n xi squared times, not times, raised to power 1/2, and C x is I equal 1 to n xi. So you add all the entries, and D, these are all examples of norms, equal to I equal 1 to n xi to the p to the power 1 over p. And p is bigger or equal to 1. Okay? If p equal to 1, you will get this one. All right? If p equal to 2, you will get this one. All right? And so forth. So all these are different norms. All right. So I'm going to do a definition and see how far we can go. Definition. So remember, we have xn plus 1 equal f of n xn with xn naught equal x naught. So this is a system. and f from 0 infinity cross d into Rn, where d is a subset of Rn. And here x belong to Rn. It's a vector. So we have a definition. The zero solution, and what I mean by that, xn equals 0 of, and this is 5.2.1 of 5.2.1. All right, A is stable, or S, if for each epsilon positive and not bigger or equal to 0, there is a delta equal delta of n naught and epsilon positive, such that x n naught less than delta implies x n n naught x naught is less than epsilon. Okay. All right. B is uniformly stable if delta is independent of n naught. Okay. C, unstable if it is not stable. D, asymptotically stable if it is stable and the limit as n goes to infinity of xn goes to 0. Okay? We can put it in absolute value here. Now, there are different stability. I recommend, if you are into stability, to read them. All right? Okay? Let's take, so I'm gonna only talk in this course about A, B, C, and D, all the way up to asymptotic stability. And we're gonna talk about the zero solution, assuming any fixed point or any equilibrium solution or any constant solution can be brought to the origin under a translation. And we talked about the translation, what it is. So you can do that all the time. So let's take a look at an example. Let xn plus 1 equal to n over n plus 1 times xn with xn naught equal to x0 different than 0 and n bigger or equal to n0 bigger or equal to 1. All right. So let's see if I can find the solution. So let's solve it. So we're gonna let Zn equal to Zn is nxn. All right. Then xn plus 1, this becomes Zn plus 1 over n plus 1 equal to Zn over n plus 1. Okay. So that implies Zn plus 1 equals Zn with Zn naught equal to n naught xn naught equal n naught x naught. So what is the solution to that one? So this has the solution Zn equals Zn naught, okay? Zn equal n naught x naught. So Zn naught, and then what is Zn naught? That is n naught x naught. So finally, nxn equal n naught x naught, which implies xn equal to n naught x naught over n, or n bigger or equal to n naught. Okay? So that is the solution. So you see, so take a quick look at it, try to understand it. I'm almost done. Let me finish it. I don't want to stop this example again. So xn is xn and not x naught, which is n naught x naught over n. This is to emphasize the dependence of the solution on n naught and x naught. Now we claim xn equals 0, okay, is uniformly stable. Okay. You see, let epsilon be positive and set delta equal to epsilon. Then look at the definition. Uniformly stable if it's independent of n naught. For x naught less than delta, all right? Yes, then for xn naught, which is equal to x naught is less than delta, we have xn, okay, which is equal to n naught x naught over n. This is less or equal to n naught over n x naught, and that is less or equal to x naught, but x naught is less than delta, which is epsilon. So delta did not depend on n naught. And why is this? Remember, the system is n bigger or equal to n naught. So n over n naught. So n over n bigger or equal to n naught. So it's bigger than 1, or n naught over n is less than 1. Okay? So it is. It's uniformly stable. Now, is it asymptotically stable? Moreover, the limit as n goes to infinity of xn and not x naught equal to the limit as n goes to infinity n naught x naught over n, and that goes to 0. So x equals 0 is also asymptotically stable. Okay? And I'm gonna stop here and I'll pick it up from here next time. I'm gonna assign homework today and grade whatever I have. All right? So please keep up. We have 2 more weeks. This week, when is the last day of classes, guys? Do you remember? Do you know?
Like, yeah, Friday or Saturday, depending on what day you want the final to be.
Not this week, next week, right?
Yeah. August 8th and 9th, I think, are the last days.
Okay, we'll see. I'm gonna try to give you the exam either on a Friday or over the weekend like we did last time, okay? All right, I'm gonna stop here. I have a couple of questions, let me see. I don't know, so is it unstable if you don't eventually end up at x naught? Yes, x naught will be unstable. That's very true. Okay. We're gonna stop the AI. I'm gonna stop recording.